This video is the second in a series on the practice of controlled drainage. The first video was an introduction to the practice, and in this video we'll talk about the design of controlled drainage systems. The learning objectives for this video are to be able to, first, understand and explain the concept of control structures for controlled drainage. Second, understand and explain the concept of water management zones. Third, understand and discuss the zone elevation interval and the design trade-offs that come with that choice. And then finally, understand and describe the differences between the design of controlled drainage systems and traditional drainage systems. There are two important concepts to understand for designing controlled drainage systems. The first is water control structures that enable controlled drainage, and the second is the concept of water management zones for controlled drainage. So starting with the first concept, water control structures are what allow us to raise and lower the outlet elevation to set and manage the height to which the water table can rise and the amount of water leaving the system. Shown here are three examples of water control structures. On the left is a traditionally manually operated control structure using adjustable stop logs to raise and lower the outlet elevation. In the middle is a float-activated pressure valve designed to hold a specified level of head behind it before opening a valve for drainage when the water level rises above that. They require at least one standard control structure at the outlet to set the base level, and then these valve structures are installed in line with the main or sub-main where a new management zone starts. The advantage of these structures are that they minimize the amount of manual adjustments that would be required for systems with multiple control structures. On the right is an example of another manually operated control structure no longer commercially available that used either stop logs or an internal standpipe for adjusting the outlet elevation. More recently, automated control structures have become available that use programmable logic controllers and power actuators to open and close one or two fixed gate valves. In combination with manual stop logs, these provide 2 to 3 outlet levels, with the top level being adjustable. In conventional drainage mode, there is no restriction, so flow through the structure is unimpeded. The flow rate is controlled by the pipe downstream from the structure. In conservation mode, water flow through the structure is controlled by stop logs or the opening and closing of a gate valve. For stop log structures, the stop logs are the same width as a control structure, with typical heights of 5 to 7 inches. As water passes over the stop log acts like a weir. The flow through the structure is now controlled by the height of the water above the top stop log and the effective length of the stop log. Gate valves will act as orifices, so orifice flow equations will apply. Since these structures hold back water, there is pressure on the inlet pipe connections, plus water will try to seep around these structures. To prevent water following the piping, use of anti-seep collars is recommended. It is also recommended to use at least 20 feet of non-perforated pipe upstream and downstream of the structure. If NRCS cost share is used, the state conservation engineer will specify what is acceptable construction. Here's an example of some anti-seep collars used to prevent water flow along the pipe and through the freshly excavated soil in the trench until the soil is able to reconsolidate. In systems that use lift stations for their outlets, the lift stations function as the control structure, and controlled drainage is done through managing operation of the pump. The second important concept is the idea of water management zones. Each control structure manages the drainage for a water management zone. One of the key decisions made in controlled drainage design is the choice of a zone elevation interval. The zone elevation interval, along with the placement of the control structures, will determine the extent of the water management zones. For illustration, using the example field on the right and the profile view on the left, if this is our drainage system layout, and we start with control structure at the outlet, the zone elevation interval is the rise in surface elevation we choose to define the extent of the water management zone for that control structure. The water management zone is then the area between the surface elevation at the control structure and the elevation from adding the zone elevation interval to the control structure elevation. So when we install our control structure and set our stop logs to our desired setting, we might ideally wish that the water table could rise to that desired depth across the entire water management zone. But obviously, water seeks its own level as it drains down to the drainage base that we've set with the outlet level in the control structure. So as we move up in elevation in the water management zone, the potential water table depth gets further from our target depth, as illustrated by the burgundy wedge. Then, if we want to add another water management zone, we can put a control structure at the top of the first water management zone and reset the drainage base for the next zone. Looking here in an example with some numbers, if this is our control structure and our targeted height of the water table rise, if the relative surface elevation in our control structure is 6 feet, and we choose a zone elevation interval of 1.5 feet, our water management zone will extend up to a surface elevation of 7.5 feet. At the control structure, we're at our target depth, and at the top end of the water management zone, we're 1.5 feet off of our target depth. So if our target depth for water table rise is 3 feet below the soil surface, we'll be at 4.5 feet at the top of the water management zone. This leads to the key design trade-off with controlled drainage design. A small zone elevation interval will be more effective with more management control, but it will mean more and smaller water management zones. Whereas larger water management zones with a bigger zone elevation interval will be less expensive, but with less management control. Typically, the zone elevation interval decision is between 1 and 2 feet. Now that we've discussed the design concepts for controlled drainage design and the key design decisions, let's take a look at how those fit into the design of a drainage management system. Looking at traditional design, we start with collecting background data such as topography, soils, crops, etc. We determine if we've got a suitable outlet and where it will be located. We choose a drainage coefficient and a drain spacing. Choose a layout for the system, then determine how that translates into actual drain depths and grades, and then potentially we'll do some iterations to come up with a layout that we like and gives us a depth and spacing to best match our choice of drainage coefficient. Then we can size the pipes, and then we're ready to install the system. For controlled drainage design, these steps stay the same, but we add an iterative step of field zoning to divide the field into our water management zones and then figure out the layout within each zone. Focusing more closely on some of those steps, the steps in blue are unique to controlled drainage, and the ones in gray are the same as for conventional design. So we need to choose a zone elevation interval, decide on our water management zones, locate the control structures, and then the next steps are all part of traditional drainage design until we get to the step of coming up with a management plan for the system. A couple of standards to be aware of, and then for additional information on controlled drainage design are the ASABE, or American Society of Agricultural and Biological Engineers, EP 479.1, which is Operation of Controlled Drainage Systems in Human Regions, and then the USDA NRCS 554 Drainage Water Management Conservation Practice Standard. Finally, it's important to remember that properly designed and installed drainage systems should last many decades across multiple generations. So as we discussed in the introduction video, controlled drainage works best on fields designed with controlled drainage in mind. So here's an example of a field in Minnesota. The design on the left was the original design with laterals running up the slope, which wouldn't have worked for controlled drainage. While planning for the drainage system, the farmer became aware of controlled drainage and worked with engineers to redesign the system for controlled drainage, resulting in the design on the right. So going back to that golden rule of drainage, for fields suitable for controlled drainage, modern drainage design should be done with controlled drainage design in mind, even if it's not going to be immediately implemented, because otherwise that opportunity is lost. So now that we've discussed design, in the next video we'll look at an example.